and today we're going to be talking about polar form of complex numbers. So in the last video we looked at how we can graph complex numbers on the complex plane. This is the real part and this is the imaginary part. But what polar form does is that it defines two things. It defines an angle and a distance. And this distance is r and the angle is theta. And rather than going some distance across and then some distance up like we would in the previous form, known as Cartesian form or rectangular form, we will just move ourselves a certain degree up and then a certain distance away. So let's start with a complex number z1. And this complex number is equal to 2 plus 2 root 3 I. And this complex number, if we're going to convert it into polar form, we need to know the distance it is away from the origin. If we were to plot this normally, we can just say that this here, where that's 2, and that is 2 root 3. So the first step that we need is to find out the distance r. So we've already had a little bit of notation that works out the distance from the origin, and that's the modulus of z1. This is also known as the radius, which is what we're trying to find out. So, what is that equal? It's equal to x squared plus y squared, all square rooted. So it's going to be 2 squared plus 2 root 3 squared. That's equal to 4 plus 12 square rooted, which is 16. Is equal to 4. So our radius is going to be 4. So let's keep that in mind. So now I want to work out the angle of the degree that we need to turn from the x-axis so we can actually move up to this point. So if we just scale this up, here's our radius, here's z1. We know that this bit here is 2 root 3, and we know that this distance here has to be 2. So using this angle theta here, we can use trigonometric ratios to actually solve for theta. So although we have calculated what r is, if we made a mistake with r, then it's going to affect our angle. So what we do is we use the other two sides. So we have an opposite and adjacent. That's just tan of theta. So tan of theta, we use our opposite, which is our y value, and our adjacent, which is our x value. And we know from the x plus yi format, we can just sub those things in. So we have this general formula here. So y is going to be 2 root 3 and x is going to be 2. These 2's cancel, so we get root 3. So theta equals tan inverse of root 3, which is equal to 60 degrees. But in polar form, we always want to have it in radians, so this is equal to pi over 3 radians. So now, to put it in polar form, what we do is we say z1 is equal, and we have these square brackets, and we put the distance first, 4, and then the angle, which is pi over 3. Then we close with these square brackets. And what we've done is we've put z1 into polar form. There is another version of polar form that actually has a good combination with this rectangular form and the polar form, and it has a very nice connection. So using this z1 example, we're going to get this new polar version. The triangle that we had earlier, this right angle, we have R, we have X, we have Y. We can work out that the cosine of this angle theta is going to equal the adjacent over hypotenuse, which is X, over R. And if I just want to, so cosine theta equals X over R. If I solve for X, it's going to become R cos theta equals X. And we can start to see where this is going. If I did the same but for sine theta equals Y over R, and then solve for Y, we can have R sine theta equals Y. And using this, we can sub it into Z equals X plus YI, and we get this new form. So Z now equals R cosine of theta plus sine plus R sine theta I, and then we can factor out the R, so Z equals the radius times the cosine of theta plus the sine of theta I. And then to make this expression a little bit simpler, we have a shortcut. But first I want to move this I out the front so you can actually see where this shortcut comes from. So this is the cosine times the imaginary times the sine. So we have Z equals R cosine imaginary sine of theta. So now we have this connection from polar to Cartesian. So what we've essentially done is we've defined a new shorthand for this expression here. So in doing so, we can convert this into this new KISS format. So using for Z1 in this new KISS format, it's going to be our distance 4, then our function, and then our angle pi over 3. Now there's a problem using this tangent here. The tan of theta does equal x over y. However, the angle that it gives us of inverse tan will only give us values in this region here, the first quadrant and the fourth quadrant. So if we had something that's in here somewhere in the second and third, we will have an angle that does not correspond to what we're trying to express. So let's do an example for the Z2, and we will call it minus 4 minus 4i. So let's get the r value of this. This is root 4 squared. Well, you could say minus 4, but squaring it's just going to get rid of it. Plus minus 4 squared. These are both 16s. 16 plus 16 is 32. We can simplify that down by factoring out. You can factor out the two 16s to get root 16 times root 2, which becomes 4 root 2. So now that we have our distance, we need our angle. But first, let's just quickly sketch where it's going to be. It's going to be, it has a negative and negative coordinate, so it's going to be somewhere in this quadrant, our third quadrant. So it shouldn't. So our tangent will give us a something that we were not expecting. So tan theta is going to equal our x value. Tan theta is going to equal our adjacent over, it's going to give us opposite over adjacent. Then we have minus 4 over minus 4, which just gives us 1. So the inverse tan of 1 is going to give us what? It's going to give us 45 degrees, or pi over 4 radians. So looking at our diagram again, we were expecting something down here, but it gave us something that's up here. So we have the right distance, but we don't have the right angle. So there's two things that we can do in this situation. Looking at where it's spat us out, it's told us that we have a distance of 4 root 2. It's told us that the angle should be pi on 4 in radians, but we know that it should be something down here. So what are we going to do? Well, we could just go and add pi over here, but we don't like that. We prefer to say that there's a negative value of there's a negative angle if our coordinate falls below our x-axis. So rather than going and getting this angle here, we get this angle instead. So if we're going to get that angle, we're going to have to subtract pi. So looking at our diagram, this is where we are, this is where we need to go. If we subtract pi, we should get where we need to be. So our angle theta is equal to pi on 4, but that's not right in this case, so we're going to subtract pi, and then we just have to make sure that they're on the right denominators. So we have pi minus 4 pi over 4, and we get minus 3 pi over 4. So now if we want to convert this into our KISS format, it's going to be Z2 equals 4 root 2 times KISS and our angle minus 3 pi over 4. Now, there's another thing that we need to take into account, and that is what's called the argument. The argument of z is just referring to theta. So for this example, it's going to be minus 3 pi over 4, but we could also say that it is equal to negative 11 pi over 4. Why? Well, I've just done a full rotation on our graph. So technically it's the same, but examiners really don't like that. You can give an infinite amount of answers if we can just add a full rotation or subtract a full rotation, because it's still negative and it's still working as it should. So examiners define a new function, the argument of z with a capital A. Now this argument of z is limited to negative pi and pi. So that way you can't get this strange 11 pi over 4. So that leaves us with one point that just doesn't fit with this range of argument of z, and that's something that's on the real axis but in the negative. So something like minus 1. So we define it as a positive pi rotation. So that's all the time that I have for complex numbers. If you have any questions, feel free to leave a comment below or contact me on social media, and I will see you in the next video.